Let's look at the next question. We have a question which says, does the position function x equals 5 plus 3 sine 4 pi t represent a simple harmonic motion? So we have to check whether this function is a simple harmonic. Okay, we know the drill. So let's write down that function. We have x, which is given as 5 plus 3 sine 4 pi t. We need to figure out whether that is simple harmonic. Okay. Alright, so what do? Well, we double differentiate this. Let's differentiate this once. I'll just put x dot because I'm lazy. I'll get 3 cos 4 pi t times 4 pi. And if I double differentiate this now, dx by dt squared, I now get 3, and that 4 pi comes out again, so I get a square, 1 4 pi, another 4 pi, and now I get a sine of 4 pi t, and I get a minus sign. So d square x divided by dt square is 4 pi square times, and there's a minus sign, times 3 sine 4 pi t. Now what is 3 sine 4 pi t? Well, what is this number? It's not x, but it's x minus phi. So this turns out to be equal to x minus phi. Now clearly this is omega, so it's omega square. But now here's the question. This does not represent d square x by dt square plus omega square into x equal to 0. It doesn't represent that form. Instead, it's representing a form d square x by dt square plus omega square into x minus some number. Let's call it as x naught equal to 0. This is the form of the differential equation we have now. Okay, and I don't even know whether that's omega anymore, because you could only call it as omega if it's in this form, but it feels like it's omega. So the question is this a simple harmonic motion? Is this SHM? Well, we can answer that with a simple trick. What we can do is, we'll ask look, the differentiation of x, which is this function, and the differentiation of just this function is the same. Do you agree? So what I'm trying to tell you is, if I take, in this case, or in any case in general, okay, if x naught is just some random number, then don't you agree that d square x by dt square is the same as d square by dt square of x minus x naught? They must be the same thing, because when you differentiate either this one or that one, this thing goes to 0, so you end up with the same answer. So just imagine, if you are only differentiating 3 sine 4 pi t, only so much, don't you think you'll end up with exactly the same answer? Correct? So since differentiation of x is the same as differentiation of x minus x naught, it's just a mathematical thing, we could substitute this over here, and we could now say that this function represents d square by dt square of x minus x naught plus omega square of x minus x naught equal to 0. And let's call x minus x naught as something. Let's call it as y maybe, or let's call it as r, whatever you want. Let's call it as x, let's call it as y. So now we can say d square y by dt square plus omega square y equal to 0. And tada, look at that, that's an SHM. So this can be written in the same form. We can write this as d square by dt square of x minus phi plus 4 pi square x minus phi equals 0. And we can call that x minus phi as some new value y. So we get d square y by dt square plus 4 pi square times y equal to 0. So yes, it is a simple harmonic motion. So the answer is yes. So what's the difference? I mean, mathematically we have proven, but what does it mean? Why am I getting a little different case over here? So all that means is, remember, in this equation, in our usual differential equation that represents SHM, x equal to 0 represents equilibrium position, right? This is the mean position. Similarly, in this differential equation, y equal to 0 is the mean position. That represents the mean position. But y is nothing but x minus phi. So x equal to phi represents the mean position. So what this is telling us is this particular function, it tells us that the particle is executing a simple harmonic motion, but it's not executing simple harmonic motion along x equal to 0. It's executing it along or with respect to, not with respect to, yeah, okay, it's executing in such a way that the mean is x equals phi. So x equals phi is the mean position. So what's going to be the extreme position? Well, the amplitude is 3. This is still the amplitude. So 3 plus phi is 8. So the amplitude on this side is x equals 8. That's the amplitude. And on this side, it goes x equals 2. So it's going simple harmonic this way. So you notice what has happened? Instead of calling x equal to 0 as my mean position, all we have done is shifted the axis and we have called x equal to phi as our mean position. Nature doesn't care what you call as your mean position. A simple harmonic motion shouldn't depend on that. So this tells us that even, so we can generalize this. Let's generalize this over here. Okay. So in general, we can say if you have x equal to x naught plus a sine omega t plus phi or something like that, then this is still a simple harmonic motion, and the only thing we need to now understand is we can rewrite this as x minus x naught as a sine omega t plus phi, and x minus x naught is the mean position. You can write x minus x naught as y equal to a sine omega t plus phi, and the mean position is y equal to 0. Therefore x minus x naught equals 0, so x equal to x naught is the mean position. That's all it is.